And just to recap for those that missed it, this is Clint Burns and Justin Lynch is over here. We're going to bring these guys in. They're on the cooling towers on a day-to-day basis.
I don't want to miss any of this brilliance.
Yeah.
So we get that right. There you go.
Brilliance right here.
These guys have seen more in their tenure about cooling towers than anybody that I know. But I thought it'd be great to just ask them some questions. I know I've been on live cooling tower assessments with these guys and have seen the details that they go through. What kind of process do you go through when you're walking up on a cooling tower about to start an assessment? I know I'm putting you on the spot here, but do you always start at the bottom and look underneath for leaks and then you go up on top, or is there a process that you follow when you're doing your assessments?
Usually when you start off going to the cooling tower, you can always tell if it's making a noise that's not supposed to be making, because it's like you start walking up to it and there's something vibrating, something going on potentially. But just kind of starting from that aspect of, hey, does something sound like it's not balanced? Is sheet metal vibrating? Kind of just that immediate, hey, does something sound out of place? And then from there, you kind of start from the bottom, walking around, explaining to the customer, hey, this is what this is. This is what this is. This is what I'm looking at. This is what I'm looking for. Have you seen anything else on the tower that looks like this? So on and so forth, kind of interacting with them so we can get feedback of, do they have a concern that they have seen themselves that they can at least point out to me, so I can say, hey, yeah, that's important. Or yes, we can address that in this maintenance that we're going to do, or this repair we're going to do, so on and so forth, and kind of go from the bottom to the top.
So you're not really just out there by yourself going to write up a report or anything. You're actually walking with the client.
Correct.
Walking with the facility manager or the director of operations and saying, hey, this is what I'm seeing real time as you're going through it.
Because it's very important for them to understand the nomenclature. Because on my proposal, if I'm saying I'm going to replace your hot water basins, and they say, well, what's a hot water basin? Oh, I call that a hot deck. I call that where the water goes in the top. Or I've never even been up there because I'm afraid of heights. Can you take some pictures? Like, it's the interaction so they can understand exactly what we're looking at, why we're looking at it, and the importance of it.
That's awesome. And Justin, I know we were at the cooling tower last week. You went inside the cooling tower and you were looking, because it was stainless. You were looking at, what were you looking for there?
So on a galvanized tower is always going to, the metal's more ductile. It's not quite as brittle. So on a stainless tower, you're going to look for cracks. That might be an issue. And if a customer has had an indication of any vibration previously, there could be a threat of cracking in the stainless. Stainless is always better for longevity, but it does come with some drawbacks. Now, when you're looking at that, we're looking up at mechanical equipment, and we happen to stumble across a pinion seal leak. So it can be common. There are many reasons why they occur, but catching it early is what's going to save a gearbox from a catastrophic failure. A pinion seal can leak a drop a day for several years, and you can maintain it with adding oil, and it's no big deal. Or you could lose that seal, and you could lose all gallon or 3 to 4 gallons, let's say, if it's in a system, within 5 to 10 minutes, and then your gearbox is gone. So
what could somebody look for when they're walking inside that cooling tower? What did you notice in that situation that said, man, we've got a leak? And you called the customer over to say, hey, look at this. He took photos, right?
Yep. We use a red oil that we put back in towers that allows you to easily identify a leak. Most oil that you see is gold, which is a little bit harder to see. Now, one thing you can look at is if a tower has a plenum walkway, when you're walking into it, you'll see water, and the oil is going to be a little hydrophobic for the water. So water drop is going to be standing, or there might be some residue if it's in a dirty area on mechanical equipment. So look for that first, and it could be an old leak, might not be a big issue, but look around, and if you see a lot of oil, you can kind of notice at the rate at which that tower is starting to leak. So if it's just a few drops on the plenum walkway, it might be a fresh leak. If there's oil in the basin all over the plenum walkway, it's likely one that's been ongoing for quite some time.
So just by looking at how much oil is it, all around, then you could tell, has this just started, or did this happen over the last 6 months and it's been ongoing? And we need to stop and check the oil level, right?
Correct.
Yeah. Gotcha. Yep. And so after that, then we went up on top of the cooling tower, and you were checking a couple other things with the water.
Mm-hmm.
Tell us about that.
So something Stephen said earlier about low flow conditions, customers often have the ability to go low flow, but they don't know it. And they'll accidentally subject a tower to a low flow condition where they'll only put, if it's a one pump per tower setup and they have 2 pumps and 2 towers, they'll run 1 pump of water over 2 cells. Well, there's no problem with that if it works for your scenario. But if you have the need for the cooling on a design day and you don't have the head pressure in your nozzle, you're going to get improper distribution. Air takes the path of least resistance. Then you start short cycling that tower. You'll get a phone call, or we will, that says, "Hey, my tower is not performing. I'm giving it less water, less duty, but it's not performing as it should." Well, we go out there and inspect, and sure enough, it is doing exactly what they said it was, but it's because it's not being operated as designed. So showing a customer you're going to need a minimum on a cross flow tower, 2.5 inches of water over that nozzle to get proper distribution, and then showing them how those nozzles operate. If they clog, what are they going to see? And then balancing water from basin to basin or cell to cell, showing them what to expect and what to see, and just a quick view of, is my tower operating correctly, can let them know that, hey, all right, we do have this issue, but we know why. So if that's the case, turn on another pump, problem solved.
Awesome. Clint, from a maintenance standpoint, what's like the top 3 or the top 5 major maintenance deficiencies that you're seeing when you're going out and looking at these towers that say 10 years old? What's the obvious things that you're seeing normally?
So we're looking at the cleanliness of the water, the cleanliness of the equipment.
Gotcha.
Obviously, cooling towers are great air scrubbers. Whatever's in the air, it's going to pull it out. Steven kind of hinted at some of that. So all the dirt and debris that gets pulled into the cooling tower, unless you have some kind of side stream filter that you're trying to filter some of that out, is cleaning your tower at least once a year, if not multiple.
Okay.
We like to recommend cleaning before peak cooling and after peak cooling. So right before peak cooling, you have it as clean as possible. Then during peak cooling, it really can't come down. Usually everybody's running it wide open because it's hot outside. People want to stay cool, so on and so forth. After peak cooling, it's pulled all that dirt and debris in there. We want to try and get that out of the system so it doesn't continue circulating. So you clean the cooling tower. Beyond that is just doing your regular maintenance checks. If you have a gearbox, checking the oil at least once a month, making sure you don't have a leak. You just kind of pop open the door, look at the front of that gearbox, make sure, hey, is it wet? Is the plenum walkway wet with any kind of oil residue?
Right.
All those kinds of things. Making sure that you don't have any weird noises going on. Because if you're out there, at least walking past it once a day, once every week, you're going to notice, hey, that didn't sound like that last week. So just putting your eyes on the equipment with what we talked about at the very beginning of this, a lot of times they're on the roof. They're out back at the facility. They're not the most pleasant looking pieces of equipment. So people kind of stick them where somebody's not going to see it. So basically,
it's kind of that out of sight, out of mind. But
exactly.
But all the while, it's actually one of the most critical pieces of the whole operation.
Exactly.
As far as the HVAC goes.
Mm-hmm.
And Justin, you pointed out, we were inside that cooling tower. You pointed out this neat little box that you said you could test it by taking a hammer and hitting the side of the cooling tower.
You sure can.
Can you explain that? And what in the world is that little box that you were showing me that day?
The vibration switch, one of the last parts in Steven's presentation, is going to be a switch that counts your inches per second that tower is going to see. And if it cycles over 0.6 inches or 0.7 is our shutdown, 0.6 is a law or 0.7 shutdown, it's going to turn the fan motor off so that tower doesn't eat itself. Older style vibration switches are mechanical and they're prone to failure, especially if the tower is in a rough environment, maybe acid process, or if it's chemically treated beyond what it should be, you're going to get a reduced life out of that mechanical switch. Now there are solid state switches or accelerometers you can put on the tower to where it'll measure the inches per second to a switch outside the tower and then feed it back to the BAS. So you get a lot more options and a lot more long-term results from those switches and much more accurate. Cost is increased, but the overall ROI, it saves the tower a lot longer. Because if you wanted to check it, you can hit it with a hammer and it should shut down. But most of the time when they don't want to work, people just cut the wires and they just run the tower without them. So the newer equipment is better because it'll give you a more accurate reading and is less susceptible to the environments inside the tower. Then people won't be cutting wires and doing things that they shouldn't.
So the main purpose of that is if the fan gets out of balance or the motor starts to get out of balance, then it'll start vibrating a lot. You don't want to have a hazard there, right?
You could lose blade tips. They could naturally come off. You could have a weather event that might damage a blade. If you're around a school, kids love to throw rocks in the cooling towers. That's always fun. See damage there. But there are other things. It could be a blade pass issue. It could be a change in tower performance that has been done to the tower, but it has not been run at full design. So if it wasn't checked when it was done, you could have an issue with blade pass, and that vibration switch will let you know that, and it'll shut it down prematurely before it does any damage.
That's awesome. But Clint, let's talk a minute about Delta T. Uh, I get a lot of questions, a lot of activity around the whole conversation of Delta T with cooling towers. Can you talk about, how do you check it? What do you look for whenever you're trying to figure out if it's actually making a good inlet water, outlet water spread there?
So we'll actually go in and take measurements at the hot water basin level to see, okay, what are you returning to the cooling tower? And then what is the cold water temperature leaving the cooling tower? Trying to look at those trends with the customer, because with the advancements and controls and technology, a lot of these customers do now have flow meters. They have basically temperature inlet, temperature outlet of their equipment. So we can look at trends at what time did they realize, hey, I'm only getting 2 or 3 degrees. And at the same time, I know getting 2 or 3 degrees, trying to get, like Stephen was saying, like you're related to your approach. If it's a 78 degree wet bulb design day and they say, well, I need 75 degree water, it's like, we can't do that. It's theoretically impossible. So figuring out the times of the year, because they could say, well, during the winter I was getting this. Well, now it's 90 degrees outside. Just making them understand how the equipment operates so that we can troubleshoot if there is a problem. Taking a look at the fill in the system of, is it dirty? Is it have a bunch of mud in it? They could be clogging the fill, and they aren't getting the performance that they once were. Start being time to talk about doing a fill replacement, bringing that tower back to like new condition thermally. So there's a lot of different things that go into it, but the more data we can get from a piece of equipment, the better.
Nice. So do you ever ask them to try to pull some of that BMS data to try to see, hey,
yes,
what was it like this time last year?
Yes.
2 years ago.
We definitely do. We try and say, do you have any historical data, or have you ever tracked it? And sometimes they're like, well, no, it's always worked, so we've never tracked it. It's like, okay, well, you need to start a benchmark of, hey, you need to start tracking
They
when
see water moving.
It's like, well,
it's working.
The cooling tower's out back. I hear the water,
Yeah.
the fan's running. I think we're good.
Right.
So we start asking for that data, and then we can dive into it. We can go back to the factory and say, hey, this is what it's doing at about this wet bulb. Is that what we would expect? Because we have a lot of information behind us that nobody else can see, that we can reach out to. I mean, Stephen is a great resource, the factory, that we can find the answers and get them taken care of.
Oh, that's great. A lot of good information there. And sweeper pipes, let's talk about that. So we were at a cooling tower that was right next to a pine forest. And if you're not from South Carolina, there are pine trees everywhere. And with all the pollen that happens during the pollen season, there's like an inch a layer of pollen on your cars. But all that also enters the cooling tower, right? Mm-hmm. And so when we got to that cooling tower, inside the water basin, there was a quarter of an inch of gunk,
Yes.
pollen and dust and just leaf matter, I guess you'd say. Yeah. What are your thoughts on that, and what can a customer do to prevent that and or keep it from messing up their system?
So in most towers, you can retrofit sweeper piping in place to help clean a basin. You can couple that with side stream filtration of sand filters, centrifugal separators, disc filter systems. There's tons of options. There's a good, better, best, and they come at different price points. But it depends upon the environment. If you've got large particulate, a sand filter, centrifugal separator won't be bad. It'll work great for you. If you've got smaller particulate and biological growth, a disc filter is going to catch a lot smaller micron component or piece. Every tower, if you put it in there, it's going to help you. If you're in a scenario where you have a permit required confined space where you can't get inside and maintenance is difficult, the sweeper piping will extend your maintenance intervals and cleaning of the tower. You should still get in it every year and mechanically clean it by hand. You never want to pressure wash media. That's a big no-no. Calcium's stronger than the PVC that it's on, so you're going to blow the media apart before you blow the calcium off.
Really?
Yes, but when you do a sweeper system, what we saw, there's still going to be some buildup in there. So imagine if that had not been in place and the amount of stuff that had been in the tower, You could be looking at downstream clogs if there's no screen or any type of filtration in line. Could be in water source heat pumps, chiller tubes, process equipment. You never know where it's going to go. So it's cheap to do it in the beginning. Always put sweeper piping in if you can, because you don't have to hook up your filtration at that point in time. You can put connections on the bottom of a tower that allow you to couple it later on. But when you want to retrofit it, it is a much harder install, best done when the media is removed from the tower, or you're going to potentially damage that bottom lift of that media. You never want to cut any media off the bottom of a tower to put pipe in place. So long term, it keeps people out of the tower, keeps it running for longer. And for those that are concerned with how a tower looks, which most of them are dirty and don't look great, it's going to make it look a lot better for the owner.
So for a new person that's new in cooling tower HVAC, they're not actually sweepers,
No.
right? Like, what is a sweeper pipe?
So the sweeper system is a network of piping.
It's not a Roomba.
No, not a Polaris in your pool or anything.
Right.
It's a network of pipes and nozzles inside of a tower. They're all fixed. They typically don't move. And they agitate the floor and they push debris and particulate that settles in the cold water basin to a common point in the bottommost sump of the tower. Then that side stream filtration typically has a pump associated with it. It's going to pull water from that bottom of the tower, suck it into a filtration system, and spit it back into the piping inside that tower of the sweeper system. And then that water just continues to cycle and side stream. You're not robbing any flow off your main portion of your tower. You could slip water if needed, but that could potentially rob GPM from process, HVAC, whatever. It's a very efficient system. It can run when you want it to. You could also have one system set up to filter one tower and then cycle between multiple different towers or cells, depending upon your orientation. But once it's installed, it's a pretty low maintenance, if not maintenance-free system. Sometimes you have to replace some nozzles. That's about the extent of it.
So it's like a permanent set of piping under the fill that shoots little nozzles worth of water out and around.
If you don't know it's there, you wouldn't. Looking at the tower, you have to physically investigate and look inside to see it.
But that's going to keep your chiller and everything else down the line
much cleaner.
Much cleaner.
Much
right.
cleaner. Yep.
And Clint, what is short cycling when it comes to cooling towers? Could you explain what it means by, like, I had never heard the term until you guys mentioned it a few months ago, but what does it mean? What does short cycling a cooling tower mean? And how could somebody not have that happen?
So when Stephen was talking about low flow, either having basin dams or nozzle cups, those are in there to make sure you have proper head pressure on the nozzles that see water. So if you have a hot water basin and only one side of that hot water basin is seeing water because it's low flow or there's minimal water, you don't have enough water going through the nozzles that then basically distribute into the fill. When you don't get that distribution of water into the fill correctly, air takes the path of least resistance and basically goes past the water where there is no water.
Gotcha.
So the side of the basin that has water, air's not crossing through there because it's going through the opposite side where there is water or where there is no water. So in effect, you're short cycling. So you have basically dry spots in your fill, wet spots in your fill, and you're not getting the thermal performance out of it. So the importance of having it designed for the low flow conditions to where your cooling tower actually performs correctly at that low flow is paramount for the equipment to operate correctly.
So basically at the lowest flow across the header, the fill stays wet all the way down. Is that the best way to say that?
So the fill will stay wet at the louver face.
Gotcha.
So you always end up putting in nozzle cups or basin dams, which block the water from going into the nozzles towards the DE face. And the reason for that is when you keep the water out at the louver face and you run the fan is going to pull that water into the rest of the fill. So you're using all your heat transfer surface.
Makes sense.
So, and like Justin was saying, it's roughly 2.5 inches of water that you want to have on those nozzles in a cross flow application because you need that proper head pressure to put the pressure onto, which we have a nozzle right here, hot water basin nozzle, which then you have a metered orifice. It comes through that metered orifice, hits that daisy on the very bottom, and then that's what distributes that water. If you don't have enough head pressure, it kind of hits that daisy and just falls off of it. And that's where you get that dry spot over here and the wet spot over here. When you get that.
The cup that
And
goes
here's
on
the
top of
nozzle
it.
cup.
Yeah.
So the nozzle will actually go into this cup, which there's some hot water basin nozzles right there on the bottom. So you can see
Good
the
timing,
daisies. Yeah, good timing. So the nozzle cup goes in, or the nozzle goes into the nozzle cup and then sits in the basin. The water level increases at low flow to a specific height based upon your GPM flow rate, but does not go over this cup. So you might have 50% nozzles that have cups and 50% nozzles that don't have cups. So the nozzles that don't have cups see water, and those are the ones at the louver face. When you get to full flow, the water level increases high enough to where it goes over the cup, and then all the nozzles in the basins, including the ones with cups, see water.
Nice. So with the counterflow, they're actually pressurized coming out the nozzle. This almost acts as like a little pressurization because you have that water pressure that's
because
pushing
you
them
need
through
the
there.
proper head pressure on the nozzle. So on a counterflow tower, your turn down, or the amount of low flow you can get down to, is a lot higher than what you can get basically turn down, or the low flow amount in a cross flow. So with a cross flow, you can usually get down to 33% of total flow, whereas on the counterflow, you can't get nearly that low because it's a pressurized spray header in a counterflow tower.
Well, this has been great. Are there any more questions on the live there?
You guys are so brilliant. No questions.
I just want to be like Tony. I just want to be like Tony.
I think I'm out of a job. You guys are awesome.
Well,
Strive to be like you, my friend.
Oh my God.
all things cooling tower, we can help you from the brand new tower to reconstructing your tower that's been there 15, 20 years. We can reconstruct it. Annual PM maintenance, we can help you with that too. So any other questions, you can reach out to us. This will be on YouTube. So thanks for watching. Hope you have a great day.